Welcome to Lesson 3, where we explore the foundation of classical mechanics, Sir Isaac Newton's laws of motion. We have two learning targets. First, you will learn to state and explain each of Newton's three laws of motion using real-life examples. Second, you will identify which law applies to different physical situations involving forces and motion. Let us see the essential question guiding this lesson. Our focus now is our third essential question, which asks, how Newton's three laws of motion explain the behavior of objects in motion. This question is about moving from describing motion to explaining what actually causes it. It is like moving from describing how fast a bicycle is going to explaining how pedaling makes it accelerate. Let us begin with Galileo's ramp experiment. Here is a classic puzzle. If a level surface could be made perfectly smooth, how far would a ball travel? If you roll a ball down a ramp onto a flat surface, it eventually slows to a stop. Aristotle believed this happened because rest is the natural state of all objects. But Galileo noticed that if you make the surface smoother, the ball travels much further. He reasoned that if we could make a surface perfectly smooth and eliminate friction, the ball would continue moving indefinitely. This was a revolutionary concept that challenged 2,000 years of belief. Newton later incorporated this very idea into his first law of motion. Isaac Newton was born in 1642, shortly after Galileo died, but his work continued the scientific shift Galileo started. By the time Newton was 23 years old, he had developed his three laws of motion. These laws completed the overthrow of Aristotle's ideas, which had dominated thinking for nearly 2,000 years. Newton published these ideas in his book Principia, which is considered one of the most important scientific books of all time. The laws describe how objects move, how forces affect motion, and how motion changes. Even today, these laws are used to explain everyday motion and large-scale motion in space. Newton was born prematurely in England and faced many challenges early on. He showed little promise at first, but his love for reading brought him back to school and eventually to Cambridge. During a plague outbreak, Newton returned home and began developing ideas that would change science, including gravity and the laws of motion. Later, he became a professor, led the Royal Society, and lived a long life devoted to scientific discovery. Newton's first law is called the law of inertia. Inertia is the tendency of things to resist changes in motion. This law states that an object will continue doing whatever it is doing unless a net force acts upon it. If it is at rest, it remains at rest. If it is moving, it keeps moving in a straight line at a constant speed. For example, pulling a tablecloth quickly leaves the dishes in place due to their inertia. Let us look at a safety application of this law. Here is a crucial pop quiz. Why must drivers always wear seatbelts? The answer is pure physics. If a car suddenly stops or crashes, the driver's body will continue moving forward with its original speed due to inertia. Without a seatbelt to apply an external stopping force, the driver could be thrown into the windshield. Let us see if this same rule applies to passengers in the back seat. Are rear seat passengers required to wear seatbelts too? Absolutely. When a car suddenly stops, the rear passengers will also continue moving forward due to inertia. Without a seatbelt, they can be thrown forward, potentially hitting the front seats, the dashboard, or even other passengers. It is a matter of safety for everyone in the vehicle. Let us look at how we measure forces mathematically. Let us define what a force actually is. A force is simply a push or a pull. It can arise from various sources, such as gravity, electricity, magnetism, or muscular effort. In physics, we measure force using the Newton, which is the international standard unit. 1 Newton is defined as the exact amount of force needed to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. When multiple forces act on an object, we add them as vectors to find the net force, which is the overall combined force. For example, if two 5 Newton forces push in the same direction, they produce a 10 Newton net force. Let us practice ranking different net forces. Let us calculate and rank the net forces on these 4 blocks, from least to most. For block A, 10 newtons left and 5 newtons right give a net force of 5 newtons. Block B has 4 newtons. Block C has 8 newtons. Block D has opposing 3 Newton forces, which cancel to 0 newtons. Therefore, the ranking is D, B, A, C. Let us look at how motion is relative to our surroundings. Motion is relative. Even when something appears to be at rest, it is still moving relative to something else. For example, when you sit still on a chair, you are at rest relative to Earth, but you are moving very fast relative to the Sun and the center of the galaxy. Motion is always described using a frame of reference, which means what you compare motion to. So when we talk about speed in everyday life, we usually mean speed relative to Earth's surface. This slide introduces acceleration and Newton's second law. Acceleration is the rate at which velocity changes over time. That change can involve speed, direction, or both. According to Newton's first law, acceleration only happens when there is an external, unbalanced force acting on an object. If forces are balanced, velocity does not change. A simple example is kicking a ball. The kick applies an unbalanced force, causing the ball to accelerate. So acceleration is not about motion itself, but about changes in motion. This slide shows how force and mass affect acceleration. When the same mass is pulled with a greater force, the acceleration increases. When the mass increases while the force stays the same, the acceleration decreases. This relationship is summarized by Newton's second law, written as F equals m times a. In simple terms, stronger forces cause greater acceleration, while heavier objects are harder to accelerate. A real-life example is pushing an empty cart versus a loaded cart. Friction and air resistance are forces that oppose motion. Friction occurs when two surfaces slide, or try to slide, against each other because of tiny surface irregularities. Even surfaces that look smooth have microscopic bumps. Air resistance works the same way, but through air instead of solid contact. Both forces act opposite the direction of motion and reduce the net force on an object. As a result, friction and air resistance reduce acceleration and can eventually bring moving objects to a stop. These examples help connect Newton's second law to everyday situations. Tugboats push with large forces, but a massive ship accelerates slowly because acceleration is inversely proportional to mass. In contrast, a hockey puck or player has much less mass, so even a smaller force can produce a large acceleration. The rocket example shows another key idea. Even a small acceleration, when applied over a long time, can result in a very high final velocity. Think about this. A gentle but steady push can eventually produce dramatic motion. The key point is that force, mass, and time together determine how motion changes. The first problem asks for the net force acting on a car, and it gives us the mass and the acceleration. When those two quantities are known, we use Newton's second law, which states that force equals mass times acceleration. So we multiply the mass of 1,200 kilograms by the acceleration of 3 meters per second squared. That calculation gives a net force of 3,600 newtons. The second problem asks us to find the mass of an object when the net force and acceleration are given. To solve for mass, we rearrange the formula to m equals F divided by a. Substituting the values, 500 newtons divided by 2.5 meters per second squared gives 200 kilograms. In the third problem, we are asked to find acceleration, and we are given the net force and the mass. Since acceleration is the unknown, we rearrange the formula to a equals F divided by m. Substituting the values, 250 newtons divided by 50 kilograms gives an acceleration of 5 meters per second squared. Let us clarify a very common source of confusion in physics, the difference between mass and weight. Mass is the actual amount of matter an object contains, and it is a fundamental measure of the object's inertia. Your mass is the same, whether you are on Earth or floating in space. Weight, however, is a force. It is the gravitational force acting on a mass at a specific location. We calculate weight using the equation W equals m multiplied by g, where g represents gravitational acceleration. On Earth, g is approximately 9.8 meters per second squared. This equation is a special case of force equals mass multiplied by acceleration. Let us calculate weight in different gravitational environments. In problem 1, a suitcase has a mass of 25 kilograms. Assuming an easy approximation for Earth's gravity of 10 meters per second squared, we find its weight by multiplying 25 by 10. This results in a weight of 250 newtons. In problem 2, we have an 80-kilogram astronaut on the moon, where gravity is much weaker, at only 1.6 meters per second squared. Multiplying 80 by 1.6 gives us a moon weight of only 128 newtons. While his weight is much smaller, his mass remains exactly 80 kilograms. In this problem, an unknown mass is suspended from a scale, giving a weight reading of 19.6 newtons. To find the mass in kilograms, we rearrange our formula to mass equals weight divided by gravity. Dividing 19.6 newtons by our approximation of 10 meters per second squared gives us a mass of 1.96 kilograms. Let us study Newton's third and final law of motion, which is the law of interacting pairs. Newton discovered that a force is not a standalone thing. It is a mutual interaction between two objects. Therefore, nature never produces a single force in isolation. Forces always come in pairs. This law states that for every force, there is an equal and opposite force. These force pairs have three key properties. They act on two completely different objects. They are exactly equal in size, and they point in opposite directions. We express this mathematically as F1 equals negative F2. For example, when you push a wall, the wall pushes back on you with equal force. Let us look at some diagrams of these action-reaction pairs. Let us analyze these common examples of action-reaction force pairs. First, look at this driving car. The tires push backward against the ground, which is the action force. In response, the ground pushes the tires forward, which is the reaction force that accelerates the car. Second, look at this person pushing a refrigerator. As he exerts a force on the refrigerator exerts an equal and opposite force back on his hands. Third, look at Earth and the space shuttle. While Earth's gravity pulls downward on the shuttle pulls upward on Earth with the exact same amount of force. Force is always a two-way street. Now, let us look at some more examples, including tennis rackets and rockets. Let us study these additional examples of Newton's third law. In diagram A, we see a launching rocket. How does it accelerate in space where there is no air to push against? The answer lies in the gas. The rocket engine pushes the hot exhaust gas downward. In response, the gas pushes the rocket upward with an equal force, propelling it forward. In diagram B, we see a tennis racket hitting a ball. The racket exerts a force on the ball, and the ball exerts an equal force back on the racket, which you can see in the distortion of the strings. In all cases, forces are mutual and paired. Let us try a quick pop quiz on these concepts. A swimmer pushes against the wall of a pool. That push is the action force. According to the third law, the wall must push back with an equal force in the opposite direction. That push from the wall is the reaction force. The reaction force acts on the swimmer, not on the wall. Let us solve this pop quiz. Question 1 asks about a swimmer pushing against a pool wall. The reaction force is the wall pushing back on the swimmer, which accelerates the swimmer forward. Question 2 asks how birds fly. The bird's wings push the air downward, and the reaction force of the air pushes the bird upward, allowing flight. Let us look at a problem involving a horse pulling a cart. Let us solve this horse and cart puzzle. A horse pulls a cart with a force of 300 newtons. First, what force does the cart exert on the horse? It is an equal and opposite force of 300 newtons. Second, if the cart experiences a friction force of 100 newtons, what is the net force on the cart? The net force is 300 minus 100, which equals 200 newtons. Let us summarize Newton's three laws. We can now answer our third essential question. Newton's laws describe how forces affect motion. First, objects stay at rest or move uniformly unless acted upon by a net force. Second, acceleration depends on the net force and is inversely proportional to mass. Third, every action has an equal and opposite reaction. These laws help us predict and explain everyday phenomena like walking, driving, or launching rockets. Let us look at our exit ticket. Here is your exit ticket for Lesson 3. Use these 3 questions to test yourself. First, state one of Newton's laws in your own words. Second, give a real-life example of that law. Third, explain how air resistance affects falling objects. If you can answer these, you have mastered our third lesson.